Good afternoon, everyone, and welcome to the ABC webinar, Transforming Wastewater to Energy for Food and Beverage Facilities. My name is Caroline P. I'm a project assistant for the ABC. First, a special thanks to our presenters who've all volunteered their time to be here today. So big thanks to Patrick Surface with the American Biogas Council and Greg Rosenberger, Jill Jordan, and Dan Cooper with Veolia Water Technologies. Thanks for your time and energy to make this webinar possible. Before we get started, just a bit of housekeeping. You should already be able to hear me and see the share screen. If you're hearing echoes or if your sound quality is bad, you can use the audio functions on the GoToWebinar toolbar, which is probably on the right side of your screen. If you still have any trouble, send the organizers a message using the chat feature, and don't worry, we are also recording this webinar, and we will send you the recording and the slides tomorrow morning. If you have a question, you may ask questions at any time using the questions pod, also in the GoToWebinar panel. We will handle all questions after the last presentation in a group discussion with all the panelists. We see lots of ABC members on the line, which is great to see so many familiar names. For those of you who aren't yet members, we're thrilled to have you with us as well. In case you are not familiar with the American Biogas Council, the ABC is the voice of the U.S. biogas industry. We represent about 220 organizations, which are a fairly complete reflection of the entire American biogas industry. If you're not a member and you'd like to engage with us and help grow the biogas industry in your business, please join the ABC through our website. For a quick snapshot of the U.S. biogas industry today, we have about 2,100 operational biogas systems in the U.S., plus several dozen standalone digesters not included on this map. And we have a significant potential for growth. We, USDA, EPA, and DOE count at least 11,000 potential new biogas systems that could be built. It's our job to work with you to realize that potential. So thank you again for joining us, and I'm going to hand it off to our moderator, ABC Executive Director Patrick Surface, to lead you through the great presentation we have for you today. Patrick, please take it away.
Great. Thank you so much, Caroline. And we are just super excited that all of you are able to join us today, because this is the most widely attended webinar, or at least for the folks who have registered for it. When I checked an hour ago, we had almost 400 people signed up for this, which makes it our largest, most popular webinar ever. So we're really excited to be able to be reaching so many folks to talk about biogas, which is, of course, a big focus of the American Biogas Council. And we hope that you'll learn a lot. And obviously, a huge thanks to Veolia, who's making this possible and made it possible for us to make this event free to you. We have sponsored webinars like this whenever our members would like to sponsor them, and that's what allows us to make them free for you. So if you're not familiar, Veolia Water Technologies is the world leader in water and wastewater treatment. They've got over 155 years of experience in the field and over 350 patented technologies which allow for comprehensive water solutions for industrial and municipal clients. We're happy because they are a founding member of the American Biogas Council and have been deeply ingrained in anaerobic digestion, mostly using their BioThane anaerobic waste and wastewater treatment technologies. With those technologies, Veolia is able to help companies solve their wastewater issues while also generating green biogas, leading to a reduction in carbon footprint. So we've got, for the presentation today, we have three presenters. We've got Dan Cooper, who's going to lead us off here, followed by a joint presentation from Jill Jordan and Greg Rosenberger. So I'm going to hand it over here to Dan in just a second. So for those of you who don't know Dan Cooper, who's the Director of Business Development for Veolia Water Technologies, he has over 33 years of experience, and his background's in chemical engineering. He successfully executed water and wastewater treatment projects for a diverse range of industrial clients, including turnkey project execution for the food and beverage industry, obviously very relevant to today, including technology selection, piloting, engineering, and commissioning. Dan's extensive knowledge of anaerobic digestion, biogas recovery, membrane reactors, moving bed biological reactors, DAFs, dissolved air flotation, solid separation and filtration, high purity water treatment technologies like ion exchange, reverse osmosis, filtration, UV, and electrode deionizations. Like what doesn't Dan do? He's very well qualified, and you'll learn a lot from him. He makes him a leading expert in industrial water and wastewater treatment. So to get things going with our program today for transforming wastewater to energy for food and beverage facilities, Dan, the microphone's all yours.
Okay, Patrick, thank you very much for the kind introduction. I'm almost amazed at how much I know based upon that, that list. But let me start with thanking all the attendees, and we're really looking forward to giving the presentation today. I'm going to do the easy part and then hand it over to my colleagues for a more technical discussion. So today's presentation is transforming wastewater to energy, focused on our anaerobic technologies for food and beverage facilities. Next slide, please. So here's our agenda for today's discussion. I'm going to start with a brief introduction of Veolia Technologies, and then go over the simple parts of what is anaerobic treatment, why do plants use anaerobic treatment, which industries, and then we're going to get into various types of anaerobic systems, how they work, talk about biogas valorization, and end with a number of anaerobic case studies. Next slide, please. So Veolia, as Patrick alluded to, is a leading water treatment company. We are a $26 billion international company focused on water, energy, and waste management. And as you can see, based upon the split of our revenues, $12 billion of water treatment revenue makes us the largest water treatment company in the world. Next slide, please. So Veolia is comprised of a number of operating groups involved in water treatment. The Veolia Water Technology Group is where we're residing, and we are the group that designs and supplies water and wastewater treatment systems for municipal and industrial users. Next. We have in our portfolio over 350 technologies which we apply to all types of industries and municipalities. Today, as you can see highlighted, we're going to be focusing on anaerobic wastewater treatment. Next. The anaerobic technology within Veolia resides within the BioThane group. BioThane is now going on 10 years since they were acquired by Veolia. They installed their first anaerobic system 35 years ago, and there are now more than 600 full-scale installations of our anaerobic systems worldwide. So we have 35 years of experience in this technology, many repeat customers, and unmatched capabilities in this field. Next. You can see here a pie chart breaking down the installation references that we have in anaerobic. Anaerobic water treatment tends to favor application in high-strength waste streams, so we see a very large percentage of our installations based in food and beverage, including brewing, and in other fermentation broth applications where you have high-strength organics. Next, please. So now we're going to go into a little bit of just the basic technical discussion about what is anaerobic treatment. Next, please. So technically, here we go. The anaerobic digestion, what does anaerobic mean? It's basically bacteria in the absence of free oxygen is anaerobic, and we're converting organic biodegradable material into biogas, a combination of methane and carbon dioxide, and producing a small amount of sludge. So we'll talk about today conversion to methane, which is where you get the energy, and also you have some conversion to carbon dioxide as part of the biogas. Next. This is a diagram of the metabolic pathway for anaerobic digestion. You have a hydrolysis, which is the breakdown of organic material into simple materials, simple sugars or amino acids. you have two steps in the digestion. We have acetogenesis, which is converting those simple materials, simple sugars, into volatile organic acids. And then you have a second step with this methanogenesis, which is where the methogens convert those fatty acids into methane. Next, please. Some simple terminology that you'll hear in all wastewater and will be used later on in the presentation. I think most people probably know the first of these, but COD refers to chemical oxygen demand, and it is the amount of oxygen required by a wastewater to oxidize all of the organic material. Biological oxidation demand, BOD, is always lower than COD, and it represents the amount of oxygen for the bacteria to biologically degrade the organic material present. Total suspended solids, I think, is self-explanatory, but that is insoluble, suspended matter, which may or may not be degradable, but it affects the design of anaerobic systems. Then we have three different acronyms that we use to describe the type of anaerobic system. We have UASB, which describes an upflow anaerobic sludge bed, and EGSB, which is a higher rate upflow system, and it's the expanded granular sludge bed. And then we have CSTR, which you can imagine is a continuously stirred tank reactor, a different type of reactor used in anaerobic treatment. Next slide, please. So some of the reasons why we would want to use anaerobic treatment for wastewater. Next, please. Some of the key drivers as to why you would want to look at anaerobic digestion. Number one would be reduction of your surcharges. Most sites are charged based on BOD or COD discharge, and anaerobic digestion can be used to reduce those. You may have that situation whether or not you are discharging to a POTW or whether you're direct discharging to a stream. Also could be part of a corporate sustainability program. But in terms of what anaerobic in particular does compared to aerobic biological treatment is that it has low energy use because it doesn't require blowers to produce a large volume of air. It also generates a much lower amount of sludge for disposal than you would in an aerobic system, and it's typically a much smaller footprint for equipment, saving your space in your plant than you would see with a aerobic basin. Next, please. So this diagram gives a little bit of an illustration of what I just said, where what we're illustrating here is if you start with 100 kilograms of COD, on the left you have an aerobic system, on the right you have an anaerobic system. You can see on the right a little bit more conversion of the COD. You have 90 to 98% COD reduction with aerobic, and you have 85% with anaerobic. But notice the amount of sludge, and you have 1/6 to 1/12 the amount of sludge produced in an anaerobic system. You don't have the 100 kilowatt hours of electricity required for the blowers. So what you have with an aerobic system is a net energy consumer and high sludge production. With anaerobic, you produce biogas, so you're a net energy producer and you produce a low amount of sludge. Next. We're going to talk more in detail about these types when I turn it over to the technical team, but in general, we're talking about high rate anaerobic systems being the UASB and EGSB, and high rate literally means it's able to be loaded at a high organic rate. The medium rate, as you might guess, would be a medium loading rate. And these are either the CSTR type or a new type using CSTR combined with membranes, which is our membrane anaerobic MBR system. And then for low rate reactors or high solids reactors, we have our traditional CSTR. Next. Next, please. The choice of which of these systems we use for a given application depends primarily on the degradability, the amount of COD concentration in the water being treated, and the amount of suspended solids that we have in the system. The first diagram is showing, we're showing all three systems, but we're describing here in the first slide the granular sludge system, which is what we get from the high rate units. They're designed for the lowest range of COD, and they're designed for lower suspended solids material. Basically, the amount of the retention time in this in a high rate reactor, the rate that we're loading this allows for excellent digestion of soluble COD and less so of suspended solids. Next, please. The middle category, where we have our medium rate membrane and biobulk CSTR, are, as you can see, designed for much higher COD loadings. We're limited to 25,000 in the high rate, and we're showing between 10 and 100,000 here for COD in the medium rate. And also on the y-axis, you can see the amount of suspended solids that's allowable in these technologies is much higher than with a high rate system. Next. The low rate system, the CSTR, is for both high concentration of COD and also very high suspended solids. This technology would potentially be used for slurries, like you might see a starch slurry, or very high fats, oil, and grease, or suspended solids. Next. Because you're in many applications, the effluent requirements will be lower than what you can achieve with an anaerobic system alone, given that your removal rate will be maybe 85 to 90% in most applications. It's very common that an anaerobic system would be combined with additional technologies to reach lower discharge limits for COD or suspended solids. And so Veolia supplies full process trains and provides full process guarantees on our systems, and many of those systems are a combination of the anaerobic systems that we're talking about today, but also coupled with physical separation equipment or aerobic polishing equipment to achieve the lower discharge limits, or potentially membrane systems to allow for water recycle from the wastewater. Next.
Thanks, Dan. We'll transition to Greg and Jill here in a second, but Dan, while I've got you here, just two quick questions. For the systems that you were just describing, are they all continuous, or any of them batch systems?
Greg's supposed to answer.
Okay, yeah. Most of these systems are continuous. All of the granular-based systems are continuous systems. They can all be continuous, I guess would be the answer. If you have a batch process that you have in your production facility, typically we have some type of an equalization tank to allow the system to be continuous. Although there are a lot of facilities out there in the food and beverage world that don't run on weekends, holidays, etc. So the good thing about an anaerobic treatment system is that it can, basically shut off during the weekend without any feed to it and be perfectly fine to start back up again on Monday morning. So we take a batch process, typically make it into continuous with equalization, but shutting down for weekends or nights, etc., is very common.
Great, thanks. And all three of them, or all three of the systems are applicable to the food and beverage industry, right?
Correct. We have systems installed of all three types in the food and beverage industry.
Great. Well, thank you. I just figured it might be easiest to just get those two basic questions out of the way that had come in while Dan was speaking here. So we're going to transition to Jill and Greg. Real quickly, let me just tell you a little bit about each of them. And Dan, thank you so much for kicking us off here and giving us a great foundation on anaerobic digestion and the technologies. Jill Jordan is a Senior Process Specialist for Veolia Water Technologies. She has over 30 years of experience in the anaerobic treatment of industrial wastewaters, including the technologies that we just heard about: upflow anaerobic sludge beds, expanded granular sludge beds, and continuously stirred tank reactors, as well as anaerobic membrane reactors. She successfully executed a multitude of anaerobic wastewater projects, taking them all from initial lab testing to on-site piloting and even full-scale commissioning. In addition to her project execution role, she also provides the technical process support to the engineering and business development teams. She also manages Veolia's Advanced Anaerobic Project Laboratory and their aftermarket services. Greg Rosenberger is the process group manager, and he's also focusing on anaerobic and biological wastewater treatment systems. He's responsible for developing solutions for industrial wastewater applications, including process selection or design, mass balances, laboratory testing, and startup of the facilities. So you can get a sense for their technical expertise here that we're going to get a taste of here in a minute. He has more than 15 years of experience in biological wastewater treatment in a broad range of industries, including food and beverage, but also pulp and paper, chemical, and ethanol industries. During his career, Mr. Rosenberger has served as a process engineer, project engineer, commissioning engineer, and project manager on a wide range of anaerobic projects. So Greg and Jill, the microphone's all yours. Take it away.
Thank you, Patrick. Can I have the next slide, please? We want to go into a little more detail about the main processes that Dan had talked to us about. So we're going to talk about the advanced biobed EGSB, which you can see a small diagram on the lower left-hand corner. The advanced BioThane UASB, which you can see on the lower right-hand corner. Our modular plants, which are in the middle. They're EGSBs, prefabricated and ready to go. And I just wanted to mention a little bit at this part that we want to mention that we're developing and working to get better control of our processes through something we call smart control, which allows for less operator involvement time and allows computer control of the system, which saves on operating costs. So if we have the next slide, please. The key to these high-rate systems is the granular biomass. These granules sort of look like caviar, as you can see in these pictures. And the key characteristic of these granules is that they contain both the methane and the acid-forming bacteria that Dan talked about. And the big thing is they have a settling velocity of 60 meters per hour, which is phenomenal. If any of you are familiar with aerobic sludge, which takes forever to settle, these granules settle like rocks. These allow for a concentrated biomass bed at the bottom of these reactors. We can get up to 10 to 12% solids in the sludge bed. This allows for a very dense sludge bed in the tanks, which allows the tanks to be very, very small compared to what you would need to treat the wastewater aerobically. And these bacteria also operate at relatively high F to Ms. We're talking somewhere in the range from 0.4 to up to as high as 1 pound per pound. That's pound of COD per pound of volatile suspended solids in the reactors. Next slide, please. Let's talk about the BioThane UASB systems first. These were the first reactors in our system. They were developed many years ago in the 1970s in the Netherlands. They're typically shorter and fatter tanks, and as you can see from this picture, the influent goes into the bottom of these reactors, and there's special feed distribution piping in the bottom so that the wastewater is evenly distributed over the area of the floor. The wastewater then filters up through the sludge bed, where most of the conversion of the soluble pollutants are converted into acids and then methane. It then filters up to a sludge blanket, which is really just a lighter density part of the biomass. And then it goes up into the settler where the sludge and the gas and the liquid are all separated. As you can see in this picture, as the three phases would grow up to the top of the settler, the gas can't get out except it's collected at the end of the settler. The sludge is heavy enough that it goes back down after it goes through the parallel plates, and the cleaned effluent goes out through the top and is collected in weirs. Next picture, please. The EGSB actually uses the same sludge as we used in the UASB. It's all granular sludge, and we can use the sludge from one to feed the other. The big difference here between the UASB and the EGSB is that the upward velocities in the EGSB are higher than in the UASB. And this is allowable because the settler is slightly different and allows for the higher upflow velocities, at the higher upflow velocities, for the sludge to be separated from the gas and the liquid. But it's the same basic principle. Most of the mixing, I should mention, in both of these reactors is done with the biogas or by the biogas. You'll notice that neither tank has any sort of mixing equipment in it. It's very simple. You put the water in the bottom. It filters up through the sludge bed. The sludge is separated at the top and remains in the tank. The gas is collected at the top of the reactor, and the clean water overflows at the top. Very, very simple, mechanically speaking. And next picture, please. We've sort of combined our original UASB and EGSB settlers and made a new advanced biobed settler, which combines the best features of the UASB and EGSB original settlers and added a tilted tube separator at the top. It's sort of like a fat lamella at the top, which allows for more of the finer particles which don't settle at the higher upflow velocities to settle back into the reactor. The key to the settler is to keep the sludge in the reactor. If the biomass is not in the reactor, it can't do the work to create the biogas which everybody wants to collect and use. So this is a picture of our newest settler with the tilted tube separator on the top. And now I'm going to turn it over to Greg to talk to you about our medium rate and membrane systems. Greg?
Hello. Next slide, please. Thank you, Jill, for your discussion around the high rate systems. So now we're going to talk a little bit about medium rate systems. As was discussed, high rate systems really are for degrading soluble COD with low influent suspended solids. So what happens if you have higher influent suspended solids and you want to treat your system anaerobically? Then you move into potentially medium rate systems. Next slide. There's two main types of medium rate systems. The first one is CSTR technology, continuous stirred tank reactor technology. This is suitable for waste streams that have a higher COD, higher suspended solids, or specifically FOG, like you see in dairies and other industries. It can be a once-through system, or we can have a clarifier on the discharge of the effluent to recycle some solids back, just like you would have in an activated sludge plant. It's sort of an anaerobic activated sludge, you could call it. So this is a technology that you would use for CODs really with high suspended solids or FOG in the influent that you do not want to remove. Next slide. The medium rate systems are really for degrading soluble COD with low influent suspended solids. So what happens if you have higher influent suspended solids and you want to treat your system anaerobically? Then you move into potentially medium rate systems. Next slide. The next generation of CSTR technology is really coupling membranes to CSTRs. And the main advantage with coupling a membrane to any biological system is that membranes are a physical barrier to sludge washout. And because of that, you can decouple the HRT, or the hydraulic retention time, to the SRT, which is a sludge retention time. So what that does is it allows wastewaters that have high suspended solids that might traditionally need to be in a CSTR that is 15 or 20 days, we can now have a reactor vessel that has 1 or 2 days of hydraulic retention time, yet still has 30 or 40 or 50 days of sludge retention time. The other large advantage to the membrane technology is it gets extremely high BOD and COD removal, where a traditional high-rate system or CSTR system might get 85 to 90%. An anaerobic MBR system has recordable BOD removal rates of 99.5% in some applications. Next slide. So what are the major benefits into looking at an anaerobic MBR treatment process? First thing is you do not have to remove the suspended solids or FOG in a pre-treatment device. So you'll see that a lot of people putting this system in are dairies or other food and beverage facilities that have high influence TSS, so would have to remove it with a DAF or a clarifier. You do not need that piece of equipment, and those solids, instead of being taken away, are digested actually in the anaerobic reactor. Two is the biomass cannot be washed out. So the biggest thing with any biological treatment plant, anaerobic or aerobic, is keeping the biomass in the tank so it can do the work. When you have a membrane system, the only way for the biomass to get out of the tank is for the operator to pump it out. So therefore, you really can't have any errors or bulking or floating layers, etc., because the membrane is a physical barrier to keeping it in. And the third major reason is it can meet most sewer surcharge limits in one step. So most sewer surcharge limits, as people know out there in the food and beverage world, are 300 BOD, 300 TSS. That is difficult to hit in most anaerobic treatment plants, but in an anaerobic MBR, it can be hit without any post-treatment. So essentially, you'll see in some case studies later, we can come in with CODs of 10, 15, 20, 25,000. And we can leave with BODs of 100 ppm with TSSs that are negligible. So essentially, you can take a multi-step process of, for instance, a DAF followed by an anaerobic treatment plant followed by an aerobic treatment plant, and you can match that effluent quality with one anaerobic MBR system. And in addition, it does make a little bit of incremental more biogas, because you're digesting all of those solids now and making that incremental biogas. So it's a very interesting system for people that have influent suspended solids that they want to digest versus removing. Next step. Next slide. So anaerobic, as we know, everybody wants to do anaerobic because of biogas. You know, we're giving this presentation for the American Biogas Council, and we need to figure out and we need to understand a little about what you do with your biogas that you generate in these anaerobic systems. So we're going to look at a little bit the different ways that people are valorizing their biogas, and then look at some of the different technologies to do so. So next slide, please. Biogas handling. So biogas gets produced in the reactors at very low pressure, usually a couple inches of water column, a quarter of a psi, and somehow they need to get into a burning device to essentially take that methane and convert it into heat or electricity. But before that can be done, there's typically 3 steps that need to occur. One is to scrub out any H2S. Any sulfate that goes into an anaerobic facility, a large portion of that gets converted to H2S, which has issues which we'll talk about in a little bit that have to be removed from the system, so typically you need to scrub it out. Second is you need to typically compress it. Generators usually require 1 or 2 pounds. Boilers might need 10 or 15 or 20 pounds, etc. So you have to compress your biogas. And the third thing typically you need to do is dry it. You know, biogas comes out of an anaerobic reactor, 100% saturated in moisture. Burning devices typically do not like moisture. So you have to remove that moisture, typically with refrigerated cooling. So when you have your biogas from your reactor, typically it's scrub, compress, dry, send to a burning device. Next slide, please. So what are people doing with their biogas in the food and beverage world? There's 3 typical things they do. The first thing they do, which we don't have on this slide, but it's been done for 25 years, is just send it to the facility boiler. Usually most food and beverage facilities need steam. They have an in-production facility boiler. The simplest thing to do, and what was done for a long time, is just to compress it and send it off to the boiler and displace natural gas that will be coming off of the grid. But about 5 years ago, that started to change into CHP generation. Why? 2 big reasons. One, generator costs keep coming down while the efficiency keeps going up. And 2, as you know, the cost of natural gas is extremely low, where the cost of electricity continues to go up. So that is pushing the economics of biogas into CHP and power generation and heat recovery. The other major reason is incentives. There's a lot of incentives out there for green electrons. Some of you might be familiar with the ITC. It's the same tax credit program that the solar and wind people get. You can get those same tax credits for green power. So most people in the food and beverage world are now looking at CHP generation as their mode of valorizing biogas produced from an anaerobic treatment facility. Veolia is very experienced in generation. We own and operate a lot of generators. We integrate generation equipment into projects that the owner wants. We are not a generator manufacturer ourselves, so we're a little technology agnostic. If the owner has specific needs for, he wants a CAD or a Yenbaka or a Guascor, we'll integrate. We will pre-package. We will just do generators in existing buildings. So we're pretty flexible there. The other main thing people are looking at now is what's called renewable natural gas or compressed natural gas. Obviously, biogas is methane. Natural gas is mainly methane. So people are looking at removing the CO2 from that biogas and then injecting it into the pipeline, or potentially trying to convert it into compressed natural gas for cars. You see a lot of people looking at that now. It again is another incentive-driven market. So when you look at valorizing biogas, you really need to look at what is right for your production facility. Is it just something simple in putting it into the boiler? Do you have need for power generation and waste heat? Can you use that waste heat to heat up your digester up into the 9,500 degree Fahrenheit range? Do you need waste heat to heat up maybe your boiler feed water? You can turn waste heat into cooling. Do you have refrigeration needs on site that could be turned into cooling? Or maybe compressed natural gas. Maybe you have a fleet of cars or trucks that you could convert to compressed natural gas, or you want to inject it into a pipeline if you have locally, and then look at how do you drive the incentive value of that gas because it is a renewable gas. Next slide. So, as I talked about before, one of the keys to biogas valorization is H2S removal. Compression and drying has been done forever. H2S removal is a little bit more tricky. There's a lot of different technologies out there to do it, and if it's not done properly, you can have some issues and concerns and really spoil some large dollar equipment downstream. Next slide, please. So why do you remove H2S from biogas? Very simple. H2S plus H2O makes H2SO4, which is sulfuric acid. So if you have an excessive amount of H2S and moisture together, it will make SO4 and it will corrode out your burning devices, which are boilers and generators, which cost hundreds of thousands, if not millions of dollars, and you don't want to do that. Another main reason is emissions, SOx. When you burn H2S, it turns into SOx, and you might have to eliminate SOx for your Title 9 or other air permit reasons. And the third reason people scrub is H2S smells. H2S smells like rotten eggs, so it's an odor issue sometimes as well. So pretty much all the time now, people have to remove H2S from their biogas. Next slide, please. There are several different technologies that can do that. They all have their pluses and minuses. Caustic scrubbing, iron sponges, carbon filters, they're in use a lot. The benefit there, typically the CapEx is pretty low, but they come with a little bit higher operating costs because you have chemicals, you have replacements of media, you have disposal of media. So the second way a lot of people do it is biological trickling filters, better for medium-sized loads. Once you get into high loads, they can get rather large, and you have to be careful of clogging. They are known to clog, and you have to go in, take them down, and remove the media and replace the media. A third way to do it is a technology that we have in-house called sulfothane. It's sort of a combination of a chemical scrubber and a biological filter. And the main benefit to it is it has a much lower operating cost, and it turns the sulfur into elemental sulfur. So you don't have to deal with a very low pH or very high pH solution or a disposal of a iron-impregnated media. So it sort of has the best of both worlds, you could say. So next slide. It's a relatively simple, straightforward system. You have a scrubbing tower where the biogas flows up through a packed bed. That packed bed has a circulating liquid around it. That is, the circulating liquid is a biological solution. It's a little small aerobic system on the side, which main purpose is to regenerate caustic. And then it will have a settler, because you make elemental sulfur. That elemental sulfur will gravity settle and decant essentially to allow for much lower disposal volume, or in some cases you can actually run that through a press, or if you have an existing centrifuge or belt press or something, can just be put in with your regular waste sludges. Next slide. So some of the key features of sulfothane. One, it can attain very high removal efficiencies, 99+% removal. H2S levels below 50 ppm, and there are systems out there that actually get below 10 ppm. You recover elemental sulfur. A lot of technologies, you always have to find out where does the sulfur go. It doesn't magically disappear. Unfortunately, if anybody has a technology that can make sulfur just disappear, that'd be a winner. But H2S in gas ends always up in some form. The positive part about the sulfothane is it ends up as elemental sulfur that can be pressed into a cake, or it can be removed with easy disposal because it's not ultra low or ultra high pH. And the other good thing is it doesn't, there's some technologies out there that inject a small amount of air. You know, air and biogas can potentially cause some safety issues if controls aren't maintained. And if you're looking at potentially converting to a green gas, air introduction has some large issues because pipeline quality gas can't contain really any oxygen in it. Next slide. So that sort of concludes a little bit of just some look at the different technologies in anaerobic and biogas treatment that are used in the food and beverage world. We're going to spend the last 15 or 20 minutes here discussing some different case studies where these are being applied in the food and beverage world. You get to see some graphs of actually how the system performs, and then we'll open up for questions at the end. So I'm going to turn it over here to Jill now to go over a couple of case studies, and then I'll finish up with a couple other case studies, and we'll have some case studies on each of the technologies that we went over today.
Thank you, Greg. Next slide, please. Okay, the first case study we want to discuss with you is at a brewery. Our technology is great for brewery effluent. For every barrel of beer that's brewed, there's about anywhere between 2 and 5 barrels of wastewater generated, depending on the brewer and their processes. So this first case study, we have a brewery that has about 1,600 cubic meters of flow a day and a COD load of about 19,000 kilograms of COD per day. The reactor is the primary piece of equipment, which you can see on the right-hand side. This is where the reactor was under construction. This reactor has an operating volume of approximately 300,000 gallons. It's 33.5 feet in diameter and 47 feet high, just for some reference. The design volumetric loading rate of this reactor was almost 17 kilograms of COD per cubic meter of digester volume per day. Next slide, please. So how is this wastewater treatment plant reactor performing? As you can see, they're getting over 90% COD reduction most days. The design influence COD concentration was approximately 12,000. They actually really run about 8,000 to 15,000, and the soluble COD is about 5,000 to 13,000. The removal rate for the soluble COD is 95%. As you can see, there's great variability in the green line, which is the influence COD, but very, very little variation in the effluent COD concentration. And this is typical for all of our high-rate systems, where the influent can vary day to day, hour to hour, week to week, but the effluent quality remains very constant. Next slide, please. The next plant I'd like to talk about is a juice manufacturer. Beverage, again, another beverage application. This is a fruit juice application. And in this case, the client had an existing aerobic facility, but their production increased, so the aerobic wouldn't be able to handle the increase in load. They therefore increased the capacity of their wastewater treatment plant by adding an anaerobic process up front of the aerobic facility. This plant was started in 2012, I should say the project started in 2012, and the plant was started up in 2013, and it was a design-build contract for us. The flow to this juice facility was 1 million gallons a day, and its load capacity was almost 25,000 kilograms per day, and the influent COD concentration design was about 6,200, with a TSS concentration of 600, and you can see the nitrogen and phosphorus and calcium numbers. The outlet, they get less than 3,700 kilograms of COD per day, or less than 930 milligrams per liter of COD. But the thing is, the performance, they're getting 85% total COD reduction. And the biogas production is 375 normal cubic meters an hour at 80% methane. And this works out to be 3.3 megawatts of gross caloric value. Next slide, please. So let's look at the process here at the juice plant in total. So we start out by screening out any gigantic solids, and then we monitor the total organic carbon content of the water, and if they have a dump or something that the total organic carbon is really high, we're going to send that flow over to a calamity tank. Otherwise, the water goes on to a DAF to remove any smaller solids or FOGs that are in the system, and the calamity tank feed is bled back into that DAF so to control the loading to the system. We then go to a buffer tank, and from a buffer tank we control the flow going into the little skinny tank, which is a conditioning tank, we call it. From the conditioning tank we go to the reactor, which is a BioBed advanced EGSB reactor. The biogas generated in this system either goes to a safety flare or to a sulfothane plant for scrubbing, and then after the gas has been scrubbed, it goes to the boiler, and the heat it goes back into the facility's boiler. The water from the advanced EGSB reactor goes into an MBBR aerobic facility, and then to a DAF to separate the solids out, and then the effluent goes to the sewer. Next slide, please. The performance here, you can see just again, you get over 90% COD reduction, and again, you can see the variability in the influence COD varies from like 2,500 up to 5,500 milligrams per liter, but the effluent soluble COD is very, very close to 400 or below most of the time. Next slide. The third case study I'd like to talk about is, again, a brewery. And what makes this special is this is a repeat customer, but the location of this facility is exceptional. The client already had one of our facilities across the valley from where this plant is, but their second brewery was the city wastewater treatment plant could no longer handle the output from the second brewery, so therefore they had to put in a pre-treatment system to handle the BOD. This plant is located in a downtown hilly location, so it was very tricky to design a plant that would fit here. And the big thing also here, this client is using the biogas and a CHP generator, and that heat is going back in to heat the wastewater and to generate electricity. The facility is designed to treat 250,000 gallons of water a day, or about 2,500 kilograms of COD per day. And they get less than 300 milligrams per liter of COD and TSS on the outlet. The BOD reduction is well over 80%, close to 90%, and the biogas production is about 21 CFM at 75% methane, which gives you 180 kilowatt hours of dual fuel to go to the dual fuel generator. Next picture, please. Here's some drawings and some figures of how close this...
Oh, back one.
Thank you. In the upper left-hand corner is a 3D design before we built the system. The building that you see behind it was an old building that had been abandoned for about 30 years across the street from the brewery. They decided to take that building and make it for a multi-purpose building. The front half, which you can't see, is now the gift shop and museum for the brewery, and the back half is the wastewater treatment plant. So they're pretty confident that there's no odors here, and the system is not abrasive or offensive to anybody in the neighborhood. The two blue tanks that you see there are the reactors. The two smaller tanks to the left are the equalization tanks, and these are our package plants. You can see the picture here, how steep the hills are here, and putting in these package plant reactors was certainly a challenge. The EQ tanks and the reactors are both 12 feet in diameter, and the reactors are 48 feet high, and their EQ tanks are 34 feet high. This plant was started up in March of this year, and within a week of starting up, the system was treating the entire brewery wastewater flow. And now I'm going to turn it back over to Greg to discuss some sulfothane and CSTR systems that we have. Greg?
Okay, thank you. Next slide, please. So we're going to look at a sulfothane case study and then a couple of anaerobic MBR case studies here. Next slide. So this is a snack food manufacturer. They have actually an anaerobic MBR facility that was built that was going to power generation. The reason they did that was they was an incentive-driven power generation, plus looking over the long term, the power cost versus natural gas cost. They also did a pretty detailed analysis on the different sulfur technologies. We looked at several different technology approaches for them, and the sulfothane technology won out via sort of a 10-year net present value evaluation, mainly due to its very low caustic usage and the ability to have elemental sulfur, which is easily disposed of. So you can sort of see the anaerobic reactor there sitting right next to the sulfothane system. The sulfothane system sits outside. This facility is located in South Dakota, so it is very cold, not an issue. The anaerobic reactor there is 48 feet tall, just for some understanding of how big things are. The sulfothane scrubber is the large skinny tower. It's about 30 feet tall. What's sitting next to it is the aerobic tank. That's about an 8-foot diameter vessel, about 12 foot tall. So next slide. So you have the scrubber column there. It's a large packed tower, about 2-foot diameter, about 30 feet tall. The reactor sitting next to it, and then you have an equipment skid that you see there on the right. That's in the building right behind those two. So it's a pretty compact system for H2S scrubbing, having 3 main pieces: the scrubber, the reactor, and a pump skid. Next slide. The design for this system was about 100 CFM. They run about 40 to 70. The gas is pretty variable. H2S coming in is pretty high, 6,000 to 8,000 ppm. And the outlet for sweet gas is less than 50 ppm. You can see some Draeger tubes on the right. They actually get non-detect, below 10 ppm H2S on most days when they control the system well, and they don't have a big spike of H2S. But this system has been up and running for the better part of 2 years, pretty consistently, and it can, if anybody wants to go see it, they allow site visitation. So I don't suggest going there in the wintertime. I was there a few December ago, and it was negative 22 degrees Fahrenheit with about 30-mile-an-hour winds. So I suggest you go in the spring or fall. Next slide. Now we'll look at a couple of case studies on the anaerobic MBR technology. We'll go over 2 main ones, one at a food producer and one at a dairy plant. Next slide. So this is a food producer that produces a wide variety of products. They probably produce 15 or 20 different lines, anything from sauces, jellies, salsa, syrups, all your different type of condiments. So the wastewater is constantly changing. Has a very high COD of about 20,000, TSS of 2,000. But the big thing is they had to meet a 300 BOD TSS sewer limit. That was a hard limit for them. They were not allowed to pay just a sewer fee above that. They had to meet that. If you get 90% reduction in a traditional anaerobic system, 20,000 times 10 is 2,000. So obviously you're not going to meet that 300. But an anaerobic MBR system can meet it. So instead of having a anaerobic system followed by an aerobic system, we had an anaerobic MBR system that met it all in one. And another thing here is when you're building your wastewater treatment plant, you don't call it a wastewater treatment plant. You come up with a fancy name, such as the process optimization and water recovery system. So that's what this wastewater treatment plant is named. Next slide. This is a 3D rendering. As you can see, when we do projects, we do a full 3D AutoCAD model that we sit down with the owner and review so they can see what their plant is going to look like before it's actually built to make comments on. You have some big reactors and equalization in the back. Inside, you have the membrane skids themselves, a centrifuge for waste solids, dewatering, and the chemical area and boiler area. Next slide. This is what it actually looks like in the full scale. You have an anaerobic MBR reactor there. It's a large mixed vessel. Behind it, you see a tank in the background there. That's the equalization tank. We sized that equalization tank relatively large for this application because they had so many different product lines that they ran. So we wanted to make sure we had a relatively homogeneous mixture going in. And everything else is inside the building for operator comfort and to allow systems to not have to have huge amounts of heat trace insulation, etc. Next slide. This is inside the building, the membrane skid there. You can see there's actually 4 membranes in parallel and 6 in series, or actually 5. So there's 2 of those skids. Those are all shop fabricated. So they're built in the shop and then sent out to the field pre-piped, pre-wired for easy installation. You also see in the picture on the left is actually looking from the opposite side. So that's the anaerobic membrane reactor in the background, and the equalization tank there in the foreground. So this system was started up about 3 years ago, 2 or 3? 3 years ago now. It's been running well ever since. The discharge from this system actually has been measured BODs of less than 50 ppm. So you come in with a COD of 20,000, you leave with a permeate BOD of less than 50. So it is running extremely well and consistent. Next slide. This is a very large dairy facility. It was a greenfield dairy along with the greenfield wastewater treatment plant. And when they built the dairy, since it was going to contain the most state-of-the-art dairy equipment in the world, they also wanted the most state-of-the-art, latest, best available technology for their wastewater treatment plant. They did a large search and a large tendering effort, and in the end, the anaerobic MBR technology, the membrane technology, was selected. So you can see the dairy, how large it is, and how tiny the wastewater treatment plant there is in the background. Next slide. As I said, this is a milk processing facility. It's located in the UK. It had a very similar situation where it had to meet some pretty stringent discharge requirements in the sewer. It's designed for about 135,000 gallons a day. The big thing here with dairy wastewater is it has high FOG coming in, which many times in most systems you have to remove that FOG via DAF. This system just can digest that FOG, and it gets COD, as you'll see in some graphs later, that is extremely low, less than 100 ppm, greater than 99% COD reduction, and they send all this gas back to the facility boiler. Next slide. Here's some pictures. You can see the digester there, actually, where it points to the digester. That's not the digester. It's the big tank on the right there. That tank on the left is actually the EQ tank. On the right, you can see the membrane skids. These membrane skids are a little bit bigger. They're 8 tall versus the other one you saw, which was 5 tall. This system's been up and operational now for about 3 years and actually went through a very large expansion. So they doubled the size of the plant about 18 months ago. So the facility ran so well for the first 18 months. When they went through their dairy production expansion, they also expanded the anaerobic plant by adding a second reactor and adding another set of membrane skids. So almost a repeat customer, you could say, in a very short period of time. Next slide. The treatment train here, some very rough screening to screen out any fibers. Fibers are an issue with membrane systems, so you want to make sure that you get rid of them before you hit the membrane. Then it goes into the anaerobic reactor with the membrane skid. The waste solids from the system are centrifuged for a cake. The biogas gets sent to the facility boiler, and there's actually a small nitrification tank. They had ammonia limits on the discharge of the system. As in the anaerobic system, any nitrogen gets converted, well, not any, but most nitrogen gets converted to ammonia. So there's a very small short retention time tank just to nitrify the ammonia before it went down into the sewer facility. Next slide. Here's a graph of the results of the facility, and I think you'll see here it's pretty remarkable. That graph on the y-axis on the left is the influence COD, which, as you can see, is highly variable. Days as low as 4,000, days as high as 28,000. So what's that? A 7-fold difference in influence COD. The red line is the effluent permeate from the system, which is on the y-axis on the right. As you can see, it's below 100 ppm pretty much every day. A couple days it might spike up to 125. But we have influence COD again from 4,000 to 28,000 variability on a day-to-day basis, with the permeate pretty much every day being less than 100. So that is the one huge advantage of an anaerobic MBR process, is it extremely steady, extremely robust, and it does not really have a huge issue with large varying influent wastewater concentrations. The effluent will remain below that 300 mark for a lot of sewer systems that they require. each day, every day. As you can also see there, about 10% of the energy consumption for the dairy comes from the wastewater treatment plant. They use 100% of the biogas that they generate. Next slide. So that ends our presentation here today on different anaerobic treatment and biogas treatment technologies that are being applied in the wastewater industry. We're going to stick around here for some Q&A as people have been chatting in the chat room there and putting some questions. We'll answer those. I'd like to thank everybody for attending this seminar and webinar. And if you have any questions or you want to contact anybody here, here's some contact information for us about your wastewater or your food and beverage facility, how we could help you out. Thank you.
Thanks, Greg. Thank you, Greg and Jill and Dan. This has been really great. I mean, I'm obviously doing stuff in biogas every day, and to be able to attend one of these webinars and learn so much is always just so great. So thank you for some wonderful presentations. I'm going to come back to this slide in just a minute for any of you that want to follow up with these folks and reach out to them, especially if your questions don't get answered today. But for right now, just two quick administrative things as we transition to Q&A. Several of you have submitted questions already, so we'll go through those in just a second. If you do have additional questions, go ahead and use the questions panel on the right-hand side. And also for any of you who may not, we're going to do questions until the top of the hour. And for any of you who take off before then, a survey should automatically pop up. Please take a minute. It's really short, and it's the only way that we have to be able to get feedback from you. So please take just a minute to fill that out. And for those of you that have recognized our challenges to getting dates right so far with this webinar, a recording and the slides will be available. We'll email them out to everyone who registered. So all those email addresses will get the recording and the slides, and we expect, just since it's the end of the day here on the East Coast, we'll probably get those out to you tomorrow as soon as we get those online. So let's go ahead and transition to Q&A. I'm going to put TJ's information back up here, just for any of you that also want to follow up with him. And just I'm going to give you a couple quick questions here, just based on what you were just talking about, and then we'll circle back to some of the ones earlier in the presentation here. One of them was regarding the dairy systems that you just had. For the dairy systems that you just covered, I assume that they're taking manure as feedstock, or was it just wastewater from any of the dairy or milk processing, or some combination?
The dairies were production dairies. They weren't dairies that were farm dairies. So these were production facilities processing the milk that came in. So there was no manure as part of the feedstock. They were all production facility wastewater.
Great, thanks. And we've got a couple questions that have come in regarding slaughterhouses, butcheries, that part of the food industry. Do you have any experience with those kinds of those projects?
Yeah, slaughterhouses, and rendering facilities obviously typically have some significant FOG and TSS coming in. So most of those rendering facilities, sometimes they use a DAF to float some stuff out, and well, it depends. Sometimes they actually float it out to no renderer, but you can do CSTR technology to do a significant amount of digestion. High rate technology is really not applicable much in the slaughterhouse industry. It's quote, really a little bit too dirty of a wastewater. So most of those technologies end up being CSTR technologies or big extended lagoon-based technologies. So we do have experience in the slaughterhouse rendering industry, with some CSTRs. We're not a real big lagoon company, to be honest with you. That takes a lot of land if you have it. But traditionally, when we look at the rendering and the slaughterhouse, we look at CSTR technology.
Thanks. Actually, that's a good segue into one of the other questions that we have, which is just generally, how do anaerobic lagoons fit into the different technologies that you talked about today?
Lagoon technology is it's an extended it's akin to typically about a CSTR technology. It's extended retention time typically. You have some level of solids digestion that occurs. The biggest thing with lagoons is you need a lot of space. They're very low loaded. So typically in production wastewater, food and beverage plants, you see some lagoons most of the time out west where they have a little extra space. They have their place in the food and beverage world. You also have lagoons that are in the manure industry. A lot of dairy manure lagoons are out there, pig manure lagoons. The biggest thing with lagoons is they're very big and they're very low loaded. They're much lower activity. So they have their place. We're not a big lagoon-based company. We built a few in our day. We try to steer people to other technologies because we don't think lagoons in the food and beverage world typically are the best technology.
Okay, I've got one more application question here, and then I've got kind of a group of questions on technology and technology limits, and then some on processing, gas processing and stuff like that. So any experience with fish or seafood processing facilities?
Fish and seafood processing. We do some fish and seafood processing. We have some experience in Europe and Asia. In the United States, I can't think of any off the top of my head. Again, you're probably looking at a CSTR technology or some upfront DAF technology to remove some of that fish waste and fish oil. We could look at it. I mean, if there's somebody out there with a fish production facility that's looking to do some digestion. We do a lot of actually fish farming work. That's maybe not fish production. I guess fish production in a different sense. Veolia is actually one of the world leaders in the wastewater treatment in the fish farming industry in Europe, and it's obviously coming to the United States as well. If we're talking about fish production facilities, I think the big issue with fish production facilities is typically they don't have a huge load. They don't have a huge amount of flow and load that needs to be treated such that they're typically treated with a little bit on-site aerobic system and some solid separation. But we can always look into see if anaerobic treatment is applicable. And we also have a large lab here in our office in South Jersey, so we can do all kinds of testing. You send us samples. We do testing on treatability. We do testing on biogas generation that can point us in the right direction of what technology best to use.
Great. So a couple questions in here on the lower limit size-wise of the technologies that you all offer. Can you quantify what the smallest end of any systems might be that you design?
Yep. We actually pushed about 6 or 7 years ago. We started doing some package plant systems with attached skids, and 2 years ago we actually went to a completely modular system, a container retrofitted out with all the equipment, pumps, control panels, MCC, shot fabricated reactor, so it's almost like a plug-and-play kit. You can probably get down to about 2,500 kilograms of COD, which is about 5,000 pounds a day of COD. It's probably the lower limit of where the economics of anaerobic make sense. Below that, probably aerobic systems just make a little bit more sense because the CapEx, OpEx situation goes there. If you don't have, you're not really utilizing biogas typically if you're down at super duper low COD levels. So concentration-wise, you typically want about 3,000 ppm, maybe 2,500, 2,000 on the low side. COD, concentration, if you have it kilograms or pounds a day, about 2,000 kilograms a day, maybe about 4,000 or 5,000 pounds a day would be the lower limit where we know from our experience below that anaerobic economics don't make sense.
That's great. You answered one of the other questions too, which is some rules of thumb for the economics for different projects. So thanks for knocking that off too. So we got a couple other questions on total solids limit. So one of the questions is, what's the total solids limit on the inflow for the UASB and EGSB technologies? We've also got got a question here involving like how do you handle or how do you optimize the plant to manage different kinds of organic concentrations? Can you talk about the TS limits on the inflow for your technology, and then how you handle different kinds of concentrations of materials?
Okay. So there's a little bit of terminology that we have to figure out here or just discuss. There's TS total solids, TSS total suspended solids. Typically, when we look at wastewater streams from food and beverage, we look at what is the COD and what is the TSS. The TS we don't look at, to be honest with you, a whole lot unless there's some huge amount of inorganic salt concentration, but very rare. So certain industries that go there. But from a TSS standpoint, really there's not much of a limit going in because there's a limit, usually about 500 to 1,500 TSS going into a granular system. If it's higher than that, we remove it with a clarification device. So there's facilities out there that have TSS of 3,000-4,000. You put a DAF in up front or some type of gravity clarifier, get that down to 500, and then put it into a granular system. If you have an anaerobic MBR system, you don't care. You just stick all the solids in. We've done work with an anaerobic MBR on stillage applications that have 25,000, 30,000 ppm of TSS. So in that sense, there really is no limit to the influent that we could handle. It's just what technology to use. Varying organic levels. As you can see from that one graph we showed, went from 4,000 to 28,000. In that sense, the influence can vary widely on a day-to-day basis. Anaerobic systems can take it. That's not that big a deal. It's really about design basis and getting a good understanding of what the variability is when we design the plant. That way we can design the proper equalization and we can design the proper size system to handle swings. Anaerobic systems, one of the benefits of them is they can really go up and down their activity rate. So you can have systems running at loading rates of 16, 17, 18, 19 for multiple days and then run at 2, 3, 4, 5 for multiple days and go right back to 18 or 19. So the influent variation is really about when we're working with the customer in the beginning, how do we define that and what is it so we can design our system to match it accordingly. Where that comes into issue is when people have spikes or large days that they don't know of, and then you design a system for 10 and all of a sudden you have a day that is 15 or 20, that's when you have the problems. But if you know those 15 or 20 days are coming in the design, we can design them out. The other thing we do now is, as we talked about, very small with the advanced control systems we have now. We now have systems that can do online COD monitoring, so we can detect spike loads as they come down to the treatment plant. We can divert them if there's a calamity tank. We can divert them to the sewer directly. We can hold them up in the Q tank. So if we have facilities that have very large load swings or existing anaerobic plants with very large load swings, we can retrofit in advanced control technology to smooth everything out.
Great. We've got a couple application questions here. So which technology best applies for these two different situations? One of them is, what's the best digester technology for wastewater effluents from recycled paper? For example, with COD between 5,000 milligrams per liter and 8,000 milligrams per liter from like effluent from wastewater or the corresponding sludge. So recycled paper.
Yeah, okay, recycled paper industry we have a huge amount of experience in. The high rate EGSB technology is what gets applied for the recycled paper industry. We have facilities in North America, Europe, Asia in recycled paper. We also, one of the other things with recycled paper is typically it comes with a high calcium concentration, potentially depending on what you're using for your feedstock source. That has been known to cause some issues in high rate systems, which we now have a calcium removal system that we can attach to it. So the EGSB technology is the technology of choice for recycled paper. I bet we have about 25 or 30 recycled paper plants around the world. It's a very large industry, for us, and we can definitely, it's perfect for granular treatment technology.
What about for a corn masa flour facility with like a high temperature and pH BOD?
That one, the corn flour, we do a lot in the corn industry, corn fermentation, ethanol. You know, in that industry, I can't remember a whole lot of corn flour industry wastewaters. I'd probably say to that person to contact us. If you have any, if you're going to contact us, if you have any analytical data on your wastewater, that always helps. A flow, a COD, a TSS, a BOD. If you don't have anything, we can help you work through what to get. High temperature, I mean, in the end, an anaerobic system typically runs at about 100 degrees Fahrenheit. So we'd probably have to heat exchange that down somehow. You know, we can get creative on influent-effluent heat exchange, with influent feed water into a production facility to try to recover that heat. High BOD, I don't know what that means. High to some people is 400, high to some people is 40,000. But again, from an upper limit standpoint, I'm not concerned that we have technologies that treat 50, 60, 80, 100,000. So I don't think we can get too high. So high temperature, that's just a matter of physical heat exchange and how best to most economically do that and recover that heat. High BOD, you know, you can put BODs up to, you know, 15, 20, 30,000 into a granular system. We can put into a membrane or a CSTR system CODs up to 100,000. So we have technologies that can treat that type of waste.
Okay, again, another application question. So what about solid food waste, where the food waste would have 10 to 100 times higher COD than wastewater? Would you just add water to it to reduce the TSS, or would you treat it differently?
If we're talking about solid food waste, we would slurry it. So we would, there's piece of equipment out there that actually can depackage if it needs to be depackaged, grind it per se into edible bites for the bacteria. It will get slurried with some water. If you have wastewater slurry with it, that's fine. If not, use clean water. Then you would go into a CSTR vessel to do that digestion. So yeah, I mean, it has to be pumpable. We have to make it pumpable, and we also have to reduce the particle size to a point where it can be degraded. So I mean, you can't take a whole apple and throw it into a digester and expect a whole lot to be done. You sort of need to turn it into applesauce before you put it into the digester to actually be able to digest that suspended solids and break that down.
So a question about economics here. There's kind of two lower limit questions. One is, and it's really just a kind of, I think, unit. So kind of a variation on one of the questions that you answered before, which is, what's the smallest, kind of the lower limit of where the systems are economically feasible? One of them is, what's the lowest kilograms of COD per day that makes sense for reasonable payback? And the other units that were requested were, could you, for like a brewery, could you put the lower limit into like barrels of beer a day equivalent?
Okay. For kilograms of COD per day, that's pretty easy. Probably in the 2,000 to 3,000 kilograms of COD per day. We have systems out there operating at with our package plant systems. Barrels per day of beer. That one I don't know I mean, I will say for the craft brewers on the line, we are working with you guys to try to figure out both anaerobically or aerobically how to treat your wastewater. You know, obviously it's a burgeoning industry. They're starting out small, they're growing, they're having wastewater treatment problems. So the interesting thing about our company is that we just don't have anaerobic technology, even though it is the greatest, best technology ever invented in the entire world, says an old anaerobic person. We do also have aerobic technology. So when we talk with somebody that might not have enough COD to make anaerobic make sense, we can give them some options evaluation, saying, okay, an aerobic plant to treat your wastewater would cost you about X dollars and have about Y dollars of operating costs. If we look at an anaerobic system, the capital is X, the operating cost is about Y, and then the owner can make a little bit of informed decisions on what is best to make their system the most economical.
So a couple more economic questions on the gas processing side of it. So with the low cost of natural gas, what's the general threshold for biogas production below which it's not really worth to treat and use the biogas? How much biogas production do you really need to make the gas chain make sense?
Gotcha. Good question. A little bit depends on what the ROI of the customer on that one, but I would say in the days before, let's say up to about 5 years ago, when the incentives really kicked in, when CHP generation really took a TV-like approach where every year it gets a little bit more efficient and costs a little bit less money. Typically, when people had less than about 60 CFM of gas, we told them that most likely the economics weren't going to work unless you really were going to stretch the ROI out. That number has been pushed down. We have people now out there with that are valorizing 25 or 30 CFM of gas now in small generation sets. If they have the key to driving the economics of a power generation CHP system is you have to find an outlet for the waste heat. In general, if you have 100 parts of energy potential in a biogas, about 40% gets converted to electric, about 40% gets converted into recoverable waste heat, and 20% goes out to stack. So if you can't figure out what to do with the other 40% of waste heat, which typically can be turned into steam, can be turned into cooling, is hot water, hot glycol, you need to figure out a way to valorize that waste heat. When you can figure out a way to do that and suck out that heat value and displace costs in your plant, that's when you can drive economics of biogas down into that 20 to 30 SCFM range.
Okay, great. A little bit more on gas treatment. What kind of steps are necessary to treat the biogas to feed it into a fuel cell, for example?
Fuel cells, they require very clean gas. Generators are a little bit, boilers typically can be the dirtiest, generators maybe the second cleanest. Fuel cells in general require some pretty clean gas. So typically those fuel cell guys want H2S levels that are extremely low. They basically almost want natural gas quality with allowing some CO2. So they want typically little to no H2S, single-digit H2S, moisture completely removed, and then compressed. So really you need to talk to your fuel cell vendor on what they require, and then we work backwards from there. To figure out what technology is best or what train of technologies are best to get the H2S and the moisture out to a level that can be put into a fuel cell.
Great, thanks. Another on post-processing, more for solid separation. For your solid separation, are you adding polymers or ferric to that?
Yeah, typically when you have solid separation, whether that's either sludge processing or anaerobic sludge or taking liquid effluent and running it through a solid separation device via a DAF, maybe via a screw press separator or something like that. Traditionally, polymer is used. If you don't use polymer, your solid capture rates are not as good. Your dryness is not as good, and typically people, the polymer pays for itself in that dryness of cake or increased solids removal. We do have some customers, for instance, that have high rate anaerobic systems that have to just polish the effluent TSS a little bit. For instance, they come out at 400, 500, 600. They just have to get below 300, so they don't need a huge removal rate. That will run very low polymer rates or no polymer rates at time during low flow. They try to optimize their polymer usage because essentially they just want to get below the limit. They don't want to get too far below the limit, because if they go into the sewer at 250 or at 50, they don't make any money or they don't save any money. So they optimize their treatment with plus or minus, basically dosing the polymer at the exact rate they need. And that takes a little bit of know-how. There's actually some new technology out there that can detect polymer in the effluent, etc., that can help optimize that better. But in general, most people plan on using polymer if you want good solids removal and you want good cake quality or float quality.
Well, this has been great. I'm sorry we do have a few more outstanding questions there, but we're at our time limit now. I hope you all got the information for TJ and for our folks here to follow up with them. We'll certainly send it back out again when we follow up with you all and send out the recordings and the slides tomorrow. And thank you very much, Greg and Jill and Dan. I'm going to turn it over to Caroline just to close things up here, but this has been great, and thank you all very much. Caroline, go ahead.
I just wanted to invite you all to our upcoming webinars. We have one next week, actually, next Friday. It's actually part 2 of our Biogas Digester Odor and Safety series, focusing on case studies. And we also have our Biocycle Refor 16 series coming up that mimics the panels that happened at our annual conference in October. So I hope you can make all those. The dates are on your screen. There's more information, and the links to register are all on our website and at /about_webinars.asp. And I just want to thank you all again for attending our webinar today. Please fill out the survey that will pop up at the end of when you close out of this webinar. And we invite you to also sign up to receive ABC-related news on our website. Thank you, and have a great day.
Thanks, everyone. Here